是吧？
发作有上下的，我意思它发上次。
他说的是发下次
那没有意见。我上回看 DSE 也是要考试的题。可能要问，石头最新的那个版本。动漫，还有看动漫的。
我小智上惨了，比小智还能小。我跟小智一样大的手才能那么大。
别说了，那你告诉我，柯南这个不会是？
小智柯南还是
关键小智长得太惨了。
他的实际的那个时间轴也才过了1年。
哎呦，我都感觉受不了。
好像就过了1年。那个柯南整个世界
就过了，我给他发。
啊？那就是这一年吗？
不可能是
这个案件
还有闪回啊？来过，忽略了这时空的重要。多在家吃。
小高。
没有，我们说的反对。啊。
还是你这种亚马逊。
好像要年龄，需要照顾。
小猫还是小狗？
小狗。
我也小狗。小猫是343。
小猫好像比较温柔，像狗1次基本因为狗是忠诚，猫是你属它，有点这个道理。猫是它是主子，狗是你是。他从心里发现你不喜欢他的。他觉得你不喜欢他。控制我，每个都抓你。
对，基本上4个
这应该是规划这个猫的方式的问题。
我没有，我就抱抱它。
不应该呀，那猫每个猫都能力的。
但是就能挠。
我先来。
啊，那你还不换成钢铁侠的钢铁战士？
不是，我觉得这个猫的好处，它突然一下不高兴。
对，它就是。
然后就。
打过这个4年，这是温顺的时候很好，温顺的就挠。
OK，结束了。
没事，猫以后来都是怕。
那你先给我说。
他睡觉了吗？没有，咱俩的嘴是他这个刺猬，生气的时候就是用刺扎我，高兴的时候肚皮让我妈肚皮。
那你为什么要惹猫生气？我就想说，那人家是不是吃我看了看。
女的嘛，
这样有
我意思想法跟这个不一样。你觉得男生觉得理所应当，他觉得不是理所应当。
刚才很抽象，那你为什么？
对，就咱思维上还是有不一样的。 很正常。也不是说惹他生气，因为你在你的想法中，这个事情是正常的，但在他想法中正常是一个，你觉得不正常，在你想法中正常，他不正常。
就看谁来回应那个。说的话有多少想法？
哎，这不是啥原则问题，最后都妥协了。
人家如果一个原则一吵架，你跟人可能吗？
没有，我俩吵架。
就一起的话，
我是天哪！这不是电影里都有。你不要这样嫌弃，人家都只是开个玩笑。一点都。哎，不理我了。
Homework 88, homework 8 is on termites. So from last time, analysis. So analysis A and A, analysis of Bernoulli. Analysis of Bernoulli processes is, I'm gonna cross that out, Poisson. Is like, similar, same. As analysis of Bernoulli. Those are the same. For Poisson, the probability that the counting process is equal to k is equal to e to the minus lambda t times lambda t raised to the power k over k factorial. The probability that there are k successes in the interval 0t is the probability of k successes in the interval 0 to t is given by this. K successes. And what would I do to find the average? I just sum this over all the k's. And the autocorrelation function T1 and T2 is equal lambda T1 plus lambda squared T1 T2. That is provided T1 is less than T2. And if it's the other way around, then just interchange T1 and T2. The telegraph signal changes. The telegraph signal we know that the probability to do the telegraph signal, we have to be able to calculate, to find the autocorrelation. What do we need to do? What is R of the telegraph signal T1, T2? Well, I pick a T1 and then I have a T2. And the telegraph signal can only go between +1 and -1. Are we okay with that? And the probability that T2 is equal to T1 means there's so many even or odd number of transitions. If it's the same polarity, even number. If the function at T1 and T2 are opposite, then it's an odd number of transitions. And so we would need the probability that transitions are even or the transitions are odd between T1 and T2. The probability that K is even is equal to sum K equals to 0, right? The probability that K is even is equal to the probability that K is 0 plus the probability that K is 2 plus the probability that K is 4 is sum from K equals 0 to 4. all the way to infinity. The probability of k successes between T1 and T2, and the probability that's even, it is equal to that sum. And that sum is, what we'd have to do is sum up these for k is odd. Or k is even, right? K is even or k is odd. So that is equal to summation 0 to 4 and so on, e to the minus lambda t, lambda times t, raised to the power k over k factorial. K equals 2, 4, and so on. The probability that there are even number of odd number of successes mean that I would sum 1, 3, 5, and so on. Let's see if I can give you the answer. The probability that k is even is equal e to the minus lambda t, COSH, lambda times t. If you look up in your calculus book, it'll give you an expansion for hyperbolic cosine. It'll also give you an expansion for hyperbolic sine. And turns out the probability that k is odd is e to the minus lambda t times hyperbolic sine of lambda t. And so we're able to do the autocorrelation function Rx, T1, T2, that's equal to, okay, plus 1 times plus 1. You know, we're doing the expected value of the telegraph signal at T1 and T2. So they can both have the same sign, plus 1. The probability that they're the same sign. Probability that x at T1 equals 1 and x at T2 equals 1. And so plus 1 okay, so plus 1, minus 1, minus 1, plus 1 minus 1 times minus plus 1 times minus 1. And probability that x at T1 equals 1, probability x at T1 equals minus 1, probability that x of T1 equals minus 1, and x T2 equals minus 1, x of T2 is plus 1, x at T2 is minus 1. So you have those 4 cases. Need to put commas. Okay, now we get back to the probabilities that, just take for example, x of t1 is 1 and x of t2 is 1. Is the probability that x at t2 equals 1 given x at t1 is equal 1. And of course the probability that x t1 is 1. And this is even. The even case. This one doesn't change polarity, and so it's the even case. So the autocorrelation T1 and T2 equals the probability that K is even minus probability that K is odd. You know, the minus sign is because minus 1 times plus 1 and plus 1 times minus 1. Those are sign changes, right? They change sign. These are the same sign. So minus 1 times minus 1, still plus 1. So those two are equivalent to the same thing. These two are equivalent to the same. Let me caution you though, because sometimes I change on the test. And instead of having something that does this, I might put on the test something that does this. Right? Then what? Then what would you worry about? Right? So from here to here, 2 changes. But you don't multiply plus 1 times plus 1, or you don't multiply plus 1 times minus 1. You'd multiply plus 1 times 0. So that means if there's a sign change, that would be no term. Right? Plus 1 times 0. So that means in this case, this number here would be equal to 0. Suppose, on the other hand, the telegraph signal does this. Still a different story, isn't it? So this could be plus 1. This might be a half. So be careful about that. So the autocorrelation is equal to T1, T2. That's equal to e to the minus lambda t times cos lambda t minus sine lambda t. Comes out. This right here is e to the lambda t plus e to the minus lambda t over 2 minus e to the lambda t minus e to the minus lambda t over 2. So that means this one and that one would go out. These two would add. Rx T1 T2 equal to e to the minus 2 lambda T2 minus T1. There it is. By the way, if you go back to the Bernoulli one and you let n go to infinity, you get the same result. So that's nice to know. So we get to a new dish. Compe. You know compe? You don't know compe? That means bottoms up. That's probably Mandarin. You don't know Mandarin. What do they speak in Hong Kong? No. Stationary. Cantonese is what they speak in Hong Kong. You know the difference between Chiang Kai-shek and Chiang Kai-shek? One is Mandarin, the other's Cantonese. Stationary process. So we're going to define things now. X of t is stationary if the joint distribution distribution does not depend on the origin. The origin. That is, for example, that's one word, fx t1 t2. That's a joint CDF. x1, x2 is equal to fx at t1 plus tau, x up t2 plus tau of x1, x2. A stationary process. And and might as well write here, Rx of T1, T2 is equal to Rx of T2 minus T1 for all T1, T2. You know, this upside down A means for all. The covariance T1, T2 is Cx of T2 minus T1. By the way, what do you think is covariance? Cx is Rx at T1, T2 minus the mean. So we found that the telegraph signal looked like this. And this happened to be T2 minus T1. Actually, the telegraph signal is e to the minus lambda T2 minus T1. But if T2 is greater than T1, then it's equal to e to the minus lambda T2 minus T1, or it's equal minus lambda T1 minus T2, right? This is T2 greater than T1. A wide sense, I'm gonna go back here. This is called strict sense. Strict sense. Strict sense stationary. So this is sometimes called SSS, strict sense stationary. Wide sense stationary. And wide sense stationary is abbreviated WSS, wide sense station. A process is wide sense stationary. S-T-A-T-I-O-N-A. It's wide sense stationary if the mean value of x of t equals a constant. That is independent independent of time. X of t and y of t are jointly WSS. If each is Let's take an example. The telegraph signal. Telegraph. Oh, let me, I need to, this is expected value of x of t is equal to that. Let's put that there. And Rx T2 T2 minus T1 wide sense stationary. The telegraph signal, is it wide sense stationary? Well, what is its mean value? X of t. Okay, if that line is along there, what is the expected value of x of t? Let's see, how much money do I have? How about $1? Going for $1. Here. What's the answer? X of t equals to, just like you can buy a bag of Fritos. Going for $1. What's the answer? You know the answer. You think it would be 1? 2? 0? nobody's gonna win $1. You think it'd be 0? I think it'll be 0. The telegraph signal. That's the probability that x of t equals 1 . What does x of t takes on? 2 values. Plus minus 1 times the probability that x of t equals to minus 1. The probability that x of t equals 1 is the same as the probability x of t is minus 1. And so the answer is 0. Suppose it takes on these values. This is 0 and 1. Expected value of x of t equals to 1/2. Oh no, is that true? It's equal to 1. The probability that x of t equals 1 plus it's equal plus 0 times 0 times the probability that x of t equal to 0. And the probability that x of t equals 1 is 1/2. Makes sense, doesn't it? X of t equals to cosine omega t plus theta. By the way, this is a stationary process, isn't it? You remember taking the probability f theta of theta equal to 1/2 pi. One. If minus pi is less than theta is less than pi, it's equal to 0 other. So 1/2 pi. 1 minus pi, and this is plus pi. You remember what f of x looks like? Remember, if you do the transformation, right here, I'll draw the cosine function, right? And and that intercepts the curve at two places. It happens to be 1 over pi, 1 over 1 minus x squared. Doesn't depend on time. Does not depend on time. So it is strict sense stationary. By the way, if something is strict sense stationary, here is SSS, strict sense. Oh, that's too big. Here is WSS. And here is SSS, strict sense stationary. Wide sense. So if it is strict sense stationary, it's wide sense stationary. And to be wide sense stationary, the mean has to be independent of time. Well, if I look at this function, I conclude from this it's WSS. It's strict sense stationary. But what about the mean value of x? The mean value of x of t is equal to 1 over 2 pi. Let me write expected value of x of t is equal to the integral minus pi to plus pi of x of t 1 over 2 pi d theta. By the way, I don't have to go and calculate the probability mass density for x of t. I can calculate the expected value using the probability mass density for the variable theta. Right. They're equivalent. So this is minus pi to plus pi, 1 over 2 pi. This would be the cosine of omega t plus theta times d theta. That integrates to 1 over 2 pi sine of omega t plus theta divided by what? Nothing, from minus pi to plus pi. Okay, so that's equal to 1 over 2 pi sine of omega t plus pi minus the sine of omega t minus pi. So this is plus pi, that's minus pi. So here's a sine function. It's kind of offset, isn't it? So omega t. Right, here's a sine. Okay, and so that distance is pi. So here's pi minus pi, pi plus pi. Oh, I think I got a mistake there. Yeah, I'm okay. So that value, this value minus that value is 0. Okay, so you don't believe it. 1 over 2 pi. This is sine of omega t times the cosine of pi. Minus plus cosine of omega t sine of pi. And that's minus, this is sine cosine, sine omega t cosine of pi, minus cosine omega t sine pi. Look, this, that equals 0. So you didn't believe my picture. What about the expected value of x squared of t? I can tell you the answer, 1/2. Did you get that answer? Who got 1/2? Okay. Time for a test. Time for a test. You got the answer? No? Nada? Who can do it? Who can do it? You got the answer. Huh? There's x of t. Theta is the random variable. Man, who's got the answer? Got 100 here. You're supposed to work on that, right? You want to do it? You want to do it here? Do you know what cosine squared is equal to? Huh? It's 1/2 times 1 plus cosine of 2 times the angle. Cosine squared theta. Did you know what cosine squared theta is? Huh? Where? Is that right? Let's see if he got this repaired. you get the right answer? Oh, he got the right answer. He got. I'm not convinced. I'm not convinced.
It's just a given function. So it's your
You got the right answer. You don't have to put your name on it. Because I'm not going to grade them. I'm just trying to determine if you're awake. Are you awake? Yes. I think this is an easy question, isn't it? What happens when we have a hard question? Okay, let's do something interesting. I am going to take so x of t is a random process. We'll say it's a current source. What is the voltage? We have a current source, x of t. We have a voltage across a parallel RC circuit. So this is the input current. So what's the voltage? C dy dt plus, this is C and this is G. Gy is equal to what? X of t? So we have a random source here is input in a parallel RC circuit. We want to know what the voltage is at that point. So that means we got to solve this differential equation. We can't solve that equation because suppose we only know, let's assume x of t is a telegraph signal. Right, it varies between -1 and +1. What do we know about that telegraph signal? We know its mean, mu x of t equals 0. We spent a little time trying to determine that. What is the expected value of x squared for the telegraph signal? That should be easy, shouldn't it? Should we have another test? We should? You're saying yes? What is the expected value of x squared of t for the telegraph signal that varies between +1 and -1? Oh, that's equal to +1 times the probability. No, that's +1 squared, right? Times the probability that x of t equals 1. Plus what? -1 squared times the probability that x of t equals to -1. What's the answer? That's a half there, isn't it? And that's a half. Comes out to be 1. So, doesn't depend on time. We spent about 5 days calculating the autocorrelation function. Rx. I'm going to write xx of t1, t2 is e to the minus 2 lambda t2 minus t1. And so that's that. Doesn't depend on the location, only depends on the difference, right? So this telegraph signal that we discussed, we didn't worry about the whether it is strict sense stationary because we didn't calculate the joint probabilities. I mean, we could spend time doing that, but we know that it is wide sense. We know it's WSS because mu of x doesn't depend on time. And E in the expected value of x squared doesn't depend on time. It's equal to 1 in this case. And the autocorrelation, so the telegraph signal is strict sense stationary. Well, what can I do with this? C. I'm going to call C d dt plus G. I'm gonna say that's a linear operator. T, where T is taking the derivatives, right? T is like taking the derivative. So, but I could have L T1 y of T1 equals to x of T1. Right, that's just the differential equation at the point T equals T1. Right? So I'm taking the derivative with respect to T1. I could also have a linear operator T2, y of T2 is x of T2. Okay, gets to the point. It gets to the point where I'm not going to be able to calculate Ry. I am not going to be able to calculate y of t by knowing that the input is a telegraph signal. It's not possible. But what I could do is calculate the mean value of y at t, y at t1 or t2. I could do that. I could also do what? Maybe calculate the telegraph. Let's make the telegraph input. I'll just write the differential equation C d dt plus G times y at T1. That's equal to the input at T1. And I have to take the derivative with respect to T1. I'm going to take the expected value of both sides. The expected value of the capacitance times D, dt1 plus G. This thing is times y at T1. That is equal to, I'll just go ahead and break it up. This is C. The derivative with respect to T1 times the expected value of y at T1. Plus G times the expected value of y at T1. That's equal to the expected value of x at T1. Well, let's just call expected value of y at T1. Let's just say that's mu of y at T1. We okay? expected value of mu of y at t1. What does that leave us with here? For the we don't know what this is, but we know what the expected value of x at t1 is equal to, and that's what? 0. For the telegraph signal, we just calculated it. So we're then left with C, D, T1, Y at T1 plus, excuse me, C, D, T1, mu of Y at T1 plus G mu of Y at T1 equals 0. There's the differential equation. Now, this particular differential equation happens to be homogeneous, doesn't it? So, what we need to know are the initial conditions on the average value. That is, what is, question, let's say mu y at T1 equals 0 is equal 0. There's no voltage on the capacitor at T equals 0. So we take the capacitor here and the resistor, we turn the current on, goes in, and we have that initial condition. Well, that differential equation, mu y of T1 is equal to let's see if we can solve that differential equation. I think we can. D mu y T1 d T1 divided by mu y at T1 is equal to minus G divided by C. We got the answer. This is ln mu y at T1 is equal to, integrate both sides here, that's equal to minus G over C times T1 plus a constant of integration. Let's call that constant. Constant of integration. And so mu y of t is e to the k, e to the k, e to the minus T1 over RC. G is 1 over R. So that's the average expected value of the random variable y. Now, if I put t equal to 0, this was T1 right here. If I put T1 equals 0, the initial condition, then the average at T1 is equal to 0, and so that's equal to 0. So e to the k would be 0. So that means that mu y of t1 equals to 0, independent of t1. We're on our way to proving that y is wide sense stationary. What else we need to do? We need to calculate the expected value of y squared at t1. We also need the autocorrelation. Next time we'll play with that.
The homework, the first question is the same as the homework 7.
Oh, that's 7. It should be 8.
No, it is homework 8, but
Oh, okay. Maybe I made a mistake.